So I thought I'd, update you on my life again. I've been learning stuff. Like and subscribe. I feel like such an idiot doing that. Dang it, Hayden, how did you talk me into this? Oh well. Alright. Welcome back. I apologize for the quick notice, but I am trying to make these videos a little shorter. I think what I'm going to do from now on is I'm actually going to try to break this up into 30-minute sections, if possible. Having an hour-long video is just, it's brutal. And going back and trying to remember information in a video, it just gets really gross. Thanks Hayden. So I'm going to try to break these up into about 30-minute sections, 20 to 30-minute sections. Yes, that does make it hard because then you have to switch between, all right, video 1, it's not video 2, but my goal here is I would like you to come back and watch these videos again at some point. I know Hayden, I know Richard asked that in the last video. That is what I want. I want to see you engaging these videos over and over again. I give you 2 lectures a week for maybe an hour, maybe as we get going in the semester, maybe an hour and a half. It may even be 2 hours full lecture a week. It's kind of gross that way, but I'm giving you a lot of material. This is a very dense class. This isn't something that I take lightly, and I really hope you don't take lightly either. So on that note, we're going to do a statics review. So we learned about in statics, primary thing in statics is we discussed what happens when systems are either not in motion or are in a constant state of motion such that there's no accelerations. Okay? Now that's important. That's really important for our sake, because if a system is accelerating, accelerations come with forces. Forces it makes the analysis a lot harder. And oftentimes what you'll see is any system that has an acceleration involved in it, oftentimes they're going to use a finite element analysis software to handle it, because the math for force transmission is really ugly. I'm just telling you how industry standards does it. It is important to understand that when an object is loaded with an acceleration, that there are forces involved there. But for a lot of this class, to make things simpler, we are not going to be dealing with accelerations. We're going to be dealing with components that are in static equilibrium. Okay? So free body diagrams are fundamental to every engineer, particularly a mechanical engineer. If you understand how to do a free body diagram, you're in a great place. It helps you deal with math, vector mechanics, everything. The steps that I usually follow to make a free body diagram is, first of all, it's important to understand, well, you draw your component in one view. Side view, front view, top view. Okay? If you're dealing with a component that deals with 3D stresses, you may need to do all 3 views. Okay? So first step is you draw your component. System or component. Okay, so let's do a free body diagram for systems. Okay? Systems are a lot easier to deal with. When we talked about our jack last time, we treated it as a system when we did our free body diagram at first. Okay? First step, you draw a system in one or more orientation. Now, how many orientations do you need to have? Well, you need to be able to view every single one of the forces that's being acted. If you can do it all with one view, great. If you can do it all with 2 views, it's harder. 3 views, you have to make sure that your coordinate systems are aligned at that point, okay? Because the big second thing is establishing coordinate systems. Okay, if you do not understand what direction X is pointing, you can pick whatever direction is X, Y, and Z, and which direction is positive and negative. But you need to make sure whatever you pick is consistent between your different views. Otherwise, your force analyses are going to be a little weird, and based on which picture you're looking at, it's just going to fall apart. You don't want to do that. Okay, so once you understand your coordinate systems, this is where what I would do usually is I like to start by instituting boundary conditions at some point, but what I would recommend for you is you start by looking at your applied forces. Okay, what forces are being applied to your system? Once you know those applied forces, then I would go ahead and I would talk about your boundary forces. Boundary forces are, as we discussed in class, they're anything that is caused by a boundary condition. Okay, if I push on this wall right now, there's a boundary condition that prevents me from falling through this wall. If I push harder, the wall pushes harder. That's it. And an applied force, what you have is that force is not based on any boundary condition. It's based on, if you have a weight sitting on top of your object, that's an applied force. That weight isn't going to increase based on how hard the ground is pushing on your design. That's not going to do anything. But that applied force is fairly constant. It is the load that causes other things to happen in the system. The boundary forces are caused because there are limited deformations capable in a system, because the system cannot move somewhere, because the system cannot rotate through some direction. There's contact with another member. That's really what creates these boundary forces. Boundary forces change based on how the applied forces change. Okay, so once you know all of these, then you have your free body diagram. Okay, once you know your coordinate system, applied forces, boundary forces, you have a system-wide free body diagram. So if I'm going to do an example with this, let's say we have I guess going with the machine design idea, let's say we have a robot, has a robotic arm that goes out like this, and then the robotic arm is picking up a 100 kilogram crate. Okay, the robotic arm is stationed right here. Well, the free body diagram for this is, let me draw this a little bit bigger. Forget it's weird that I'm writing on a board. So got this station, got this thing, got one of these, got a box. This box is 100 kilograms, which is 981 newtons. Okay, we'll say this reach distance here is 2 meters. Okay. Oh, dang, I forgot to talk about moments. I knew I was missing something. My apologies. So you have 2 meters distance between the mounting point for your robot and the point of application of the load. Okay. We'll go ahead and say that at this moment in time, this is 1 meter above the ground. Okay. If we're looking at the system-wide free body diagram, a system-level free body diagram, I don't care what forces are in here. I'm only looking on forces that are acting from outside the system on the system. Okay? Now what does that mean? Well, here's my system right here. It's this robot. That's what I'm considering my system. Outside of that system exists gravity. The world, the earth, pulls on this in a force where this system in general has some kind of gravitational pull on it. And it's going about the center of gravity, which is about right there, maybe a little bit closer here, maybe even somewhere out in space here. It's wherever the center of gravity is, but that force of gravity is pulling the system downward. Okay? Similarly, again, since the system is just the robot, you have this force pulling up. Now, if we included the box as a part of the system, the force of gravity would be moving over, and the weight of this would be included in that force of gravity. You end up actually getting the same moments on this area, but that's whatever. It just makes the math harder, in my opinion. I'm going to go ahead and take this, make this be an applied load. W, 981 newtons. This is going to be my ground force in the Y direction. There is no ground force in the X direction because there's no X forces. But there is going to be a moment that is applied to counteract this weight. Because again, you have this force exerted along this axis, this axis, this axis. All of these axes are parallel, but they're not in line with each other. So there is going to be a moment. Okay, so that moment is counterbalancing the fact that this weight, if you were to pick up something heavy and hold it in your hand, okay, the heavier that gets, the more it makes you want to tip over. Well, that's basically what this is doing right now. The heavier this is, it's causing it to rotate this direction. Okay, it's rotating about the force. If you use your right hand rule, you slap your fingers on the vector here, you curl your hand in the distance vector from this vector to the point of application of that force, and your thumb is pointing in the direction that it rotates. It is curling this way. Okay? We have to apply a counter force, where thumb is now pointing out of the board, in order to counter that. So we know that M is going to be in that direction. Okay, so this is our free body diagram. Now we can do the sum of the moments. We can do the sum of the moments in the X direction, Y direction, some of the forces, and then some of the moments if needed. Now for more complex systems, you will have to do some of the moments, some of the X, some of the Y, some of the Z. You'll end up with as many as 6 equations that you're using simultaneously to solve a system. So it does get more and more complicated. Excuse me. So what about components? Well, if we're going to talk about free body diagrams for components, it does change a little bit. Because free body diagrams for systems are fairly straightforward. We're used to doing that in statics. But as we talked about in class last week, when it starts getting down to the component level, things get a lot uglier. We're not looking at just gross systems anymore where you have one free body diagram that's great. No, you have to draw free body diagrams for every single component now, and that can be really ugly. I'm not gonna lie to you. It's one of the challenges of this class. So we're gonna deal with free body diagrams of individual components. Why do we need to do that? Well, I can tell you this. Based on this information right here, you have no idea whether or not the system is going to fail. We assume the system is strong enough to be able to handle this. But in reality, this arm, even maybe this string could be too weak to be able to handle any of those forces. So when we do individual components, what we're doing is we're establishing forces being transmitted through those components, the loading conditions on those components, such that we can begin to analyze the stresses on those components. Why do we need to know the stresses? Because we need to know if those stresses are so high that it is causing the component to fail. Okay? I want to make sure that the stresses on you are not too high that it causes you to fail this class. But I mean, it's life, so I'm not too concerned. Okay, so when we're talking about individual components, the first thing you have to do a system. Free body diagram. Okay? The first thing you have to do is this. That's step one. Now, what you need to do is you need to figure out the kinds of connections between components. Okay, so that matters about how forces are transmitted. If this is a string, strings cannot carry a moment. Strings cannot carry a horizontal force. Strings cannot carry a compressive force. Strings only work in tension. Okay? And that matters. That's important to the way our system is analyzed. So we can't just simply say, well, let's just throw a, there may be X, Y, Z, M forces all transmit, M, X, X, M, Y, Y, M, Z, Z moments translated through this joint. It's just possible. It's just going to happen. You do that, you're going to overwhelm yourself with formulas. It is extraordinarily overwhelming. So, best thing you can do is start with the first component that is loaded with some outside force. Okay, look at where an applied force is. Or if you figured out what the force in the moment is here, go to there. And this is a boundary force. Pick either an applied or a boundary force and the component that it directly acts on. Okay, and that's what I'm going to go ahead and go to first component. Okay, first meaning it is the component that has an applied force on it or a boundary force on it that you know. Here, it'd be easiest for us to start with this one, because we know what this applied force is. Okay? Next, draw that component by itself. Now, here's the thing. You may need multiple orientations. You may need a front view, a top view, a side view. You may need all of those. Okay, once again, what was in the last one, right after we drew a component, we had to figure out coordinate systems. Okay, the nice thing about coordinate systems on a component are you can make your coordinate system as long as it's consistent for that one component. And as long as the force vectors from one component to the next component are facing the same direction, you can use whatever coordinate system you want on each component. It does make nice, because what they oftentimes do in robotic arms is they will make the coordinate system in line with the arm. Yes, you learned how to shift coordinate systems in dynamics class. Or you should have. It's kind of one of the big points of dynamics. So for your part, establish a coordinate system. Okay, 5. Add applied forces. Again, your applied forces are usually given on some direction and some angle. Okay? I'm going to add in this one too. Add your boundary conditions. Boundary forces. If you knew them from the system, see step 1. Okay, it should be from there. You should have them already. Okay, once you've applied these, which we have one applied force here, we have forces that are being transmitted through joints. And the joint forces are really where the difficulty comes in. what kind of forces can be transmitted through this joint? Well, if I were to take this component, let's say I'm going to label this 1, this will be 2, and this will be 3. Okay? I'm just going to draw 1 now. Here's 1. This experiences this kind of a force. I can make this coordinate system be whatever I want, but I'm going to go ahead and say that this is X and Y. Now, here's the problem. I don't know how to write letters. That's the problem. No. Here's the problem. I don't have any X direction forces. I have a joint right here. It has to carry a Y direction force. It has to. The joint forces are only applied at specific locations and joints. Okay? Which you could even consider those specific locations to be joints. They're also applied at center of gravity, but that's different. Okay? Forces are only applied at joints, center of gravity, and boundary locations. Okay? This application force, this applied force, is a joint. That's what it is. If I touch the board, I've created a joint between my finger and the board. Yes, I'm using a loose definition of joint, but you got to think of joints that way. Forces are only applied at joints, meaning there's a contact at the center of gravity, which is usually happen through force of gravity or through a magnetic force, and at boundary conditions, which is another joint. I'm writing joint so much. Why isn't it April 20th? That was terrible. I apologize. When we talk about all of these now, you also have to now do your force summaries for the X, Y, Z directions on your components based on the loading conditions that are given it. And you need to figure out what these joint forces are. Figure out what these boundary conditions are on those components that are creating those forces. You have to do that. You have to. Once you know what forces are required out of your joints, you then take these joint forces and you apply it to the next one. Okay? That is, it goes into this step for the next component. Those forces are equal and opposite on the other side. When we draw a tension force, so this one's lifting upward. When it goes to point 2, that same force is going to be flipped. Equal and opposite. It's going to be downward. These two have equal magnitude, but opposite direction. Because if this is being lifted up by something, well, this is being pulled down. If I grab onto my hand and I pull down on it, this hand has to pull up to make it happen. I am exerting a downward force on this hand, but this hand is exerting an upward force on this one. Those are the equal and opposite forces. That's how the forces pair. Okay? So when it comes down to doing individual components, yes, it gets more complicated. Yes, you have a lot more math. You need to look at it component by component. Look at the joints. Look at how the joints are reacting. Those are the unknowns that you can't figure out. And once you know the joints, you can figure out the forces that are being transmitted through the object. And once you know that, you can figure out the stresses. What is the next step of this class? It's figuring out stresses. So yes, you are going to need, I'm going to go ahead and call this J1, Y, because that's joint 1, joint 2. This is going to be MJ1, and it is in the ZZ direction. So MJ1ZZ, that's really gross. We're going to be doing more examples coming up in the future. I will be expecting you to know this at some point. We are going to step through these examples at some point too. But I'm going to go ahead and be done with this lecture. Please suggest a catchphrase for me at the end of these videos, because I am the least catchy person. Engineering is fun! Except I just lied to you. Except it is kind of fun. I love knowing how things work, and I love knowing how to understand things and analyze things at a very deep level. So, okay, bye!